Ever since the invention of the first computer by Charles Babbage in the 1830s, which could automate tedious astronomical calculations to be used in navigation, the computer has come a very long way in a very short time. With every passing year, computer parts get both smaller and more powerful, and it seems as if we are reaching the limits of the classical computer. So the question arises, what's next? In 1980, physicist Paul Benioff, a pioneer in the field of quantum computing, proposed the first theoretical model of the quantum computer, an improvement on the Turing machine. In his work, he showed that a computer could work under the laws of quantum mechanics, exploiting the properties of quantum states, such as superposition and entanglement. His theory gained a lot of traction in the scientific community, encouraging others to conduct further research on the topic. David Deutsch, in particular, served a key role in highlighting the potential of quantum computing by proving that a quantum computer can perform calculations at speeds that far exceed anything a classical computer is capable of. Classical computers use bits to store data. In the physical world, the bit represents the two states a transistor can be in. 1 means that the electrons can flow through the transistor, while 0 means the electrons are being blocked. The data can then be processed using logic gates to carry out calculations. However, with quantum computers, qubits are used to store data. They can be a photon, an electron, or a semiconducting material. Unlike the traditional bit, a qubit can exist in both on or off states at the same time. The different properties of the qubit, for example the polarity on a photon, allows it to be in a combination of both states at once. The value of the qubit cannot be predicted until it is measured, at which point it decides between one of the two definitive values. This is quantum superposition. On its own, it's no different than using a traditional bit, but when coupled with the entanglement property, they become far superior. When a qubit is entangled with another qubit, finding the value of one of those qubits will immediately tell you the value of the other. For a classical computer, finding all the possible calculations of a circuit can only be done by repeating the process multiple times using different inputs. But with entangled qubits that are in superposition, all the combinations are calculated in one go, and it's just a matter of picking the answer you want. This makes quantum computing incredibly fast and brings things that were out of reach in the past into the realms of possibility. As exciting as this is, it is estimated to take at least until 2030 for quantum computers to be viable. Several machines have been made thus far, and they all prove quantum supremacy, the ability to process computations faster than a classical computer. Developments could allow quantum computers to one day be used for simulation of molecules, financial modeling, more accurate weather forecasts, and many more things. Currently, there are many obstacles in the way, such as long-term data storage and the fact that they can't operate at room temperatures due to the interference heat causes on the photons that are processing data. The machines have to be kept at close to absolute zero to provide accurate results. There are also security risks that come with developing computers that are this powerful. Security encryptions that take thousands to millions of years to crack using a classical computer could hypothetically be cracked in a few hours or days using a quantum computer. The future of quantum computing is as unpredictable as the quantum world itself, but with the rapid developments and many great minds working together on this problem, the world of science fiction could soon become our reality.